Thank you very much. Thank you for coming in large numbers to hear about black holes. So I've got an hour to take you to the very edge of our understanding of black holes. So what I want to do is, first of all, describe the old-fashioned picture of a black hole, by which I mean primarily Einstein's picture, which is an idea that's existed for, well over 100 years now. But then in the last 10 minutes or so, I might go a bit mad because I want to talk about recent work, so work that's been done 2019, 2020, and is still being done on solving what's become known as the black hole information paradox, which is one of the most, I think, exciting areas in modern theoretical physics that was really stimulated by work that Stephen Hawking and colleagues did back in the 1970s. So I'd like to get there in the last 10 minutes or so. But first of all, I want to talk about black holes as Einstein's generation would have understood them. So I have an image here, eventually. This image, and what I asked, by the way, for all the lights to be dimmed, because I thought you didn't want to see me, you wanted to see the pictures. So if you object to that, then I apologize. But they will dim the lights, I think, at some point. Go on. There we are. This image, as I talk about black holes, I hope you agree things are going to get stranger and stranger. But I wanted to emphasize right at the beginning that these things are real. They are naturally occurring objects. There are millions, billions indeed, these things in the Milky Way galaxy alone, and we have photographs of them. This is the first image ever taken of a black hole. It's a radio telescope image a few years ago, taken by a collaboration called the Event Horizon Collaboration. And it's an image of a black hole that's in the center of a galaxy called M87. It's 55 million light years away. And this black hole, it's called a supermassive black hole, is 6 billion times the mass of our sun, which is why it's called a supermassive black hole. Just to set the scale, that means that this image is probably 3 times the diameter of our solar system, or something like that. But if you think about it, having 6 billion times the mass of the sun condensed into this relatively small area is an astonishing thing. And as I'm going to show you a little bit later, the interpretation of this image, according to Einstein, is that you are looking at a photograph of the end of time. So these are very strange things indeed. The idea behind them, in order to describe them, I need to teach you a little bit, a tiny bit, of Einstein's theory of general relativity. Now, we usually teach that in the 4th year at a university lecture course. It takes 40 lectures to introduce it, but we're going to do it in about 2 minutes. But we're going to focus on the most important bit. The basic idea of Einstein's theory of gravity is very simple, and it's often represented like this, a kind of an image of, in this case, the Earth, distorting something. That something is often referred to as the fabric of the universe. We call it space-time. So Einstein's great insight was that everything in the universe distorts space and time, and everything in the universe responds to that distortion. So in this image, you could imagine, if that's the Earth distorting the fabric of the universe, you could imagine the moon passing by the Earth, and it won't go in a straight line because it's traveling through distorted space and time. Its path will be deflected. And if you send it in the right way, it will be deflected into an orbit. So Einstein's picture of gravity is not like Newton. It's not that there's a force between objects that pulls them together. It's that objects are responding to the distortion of the fabric of the universe caused by other objects. The great physicist John Wheeler put it very beautifully. He said, matter tells space-time how to curve, and space-time tells matter how to move. That's Einstein's theory, and that's all we really need to know. I can show you a picture of this in action because just a few months ago, the James Webb Space Telescope sent this image back from space. It's one of the first images that new space telescope took. And it's an image of a cluster of galaxies. So you're to imagine a dense cluster, hundreds of galaxies in the mid-ground of this image. And then obviously there'll be a lot of galaxies further out into the universe. And so the light from the distant galaxies is passing through the distorted space-time, distorted and warped and curved by the intervening cluster of galaxies, and then entering the space telescope. And you can see that distortion. You can see all sorts of strange shapes and curves here. It's almost like you're looking at the universe through a wine glass. But the wine glass here is space and time distorted by the intervening galaxies. It's called gravitational lensing. So Einstein would have loved this image because that is a photograph of general relativity in action. So now let's go to black holes. The idea actually behind black holes goes back way before Einstein. It goes back to the 1780s, 1790s. So the great French mathematician Laplace and actually an English clergyman called Mitchell had roughly the same idea, independently, we think, at the same time, which is they were thinking of something called escape velocity, which is the speed you have to travel to completely escape the gravitational pull of something. So for example, from the surface of the Earth, you have to travel at around 11 kilometers per second to escape the Earth's gravitational pull. It's quite fast. Maybe you go bigger, so let's say you go to something like the Sun, for example, much more massive than the Earth, much larger than the Earth. The escape velocity at the surface of the Sun is more like 620 kilometers per second. So I suppose amongst your many problems, if you're sat on the surface of the Sun, one of them is getting off, right? 620 kilometers per second. What Mitchell and Laplace thought is, well, what happens if you keep going? So can you imagine that there are stars in the universe that are so massive, so enormous, that the escape velocity exceeds the speed of light? And then, Laplace reasoned, you wouldn't be able to see them because light couldn't escape. And so he called them dark stars. And there's a wonderful quote actually in the paper he wrote, I think it says 1787, where he said, "The largest objects in the universe may go unseen by reason of their magnitude." So dark stars. Now, today we know that such things don't exist. However, what Mitchell and Laplace missed is that you can also increase the escape velocity at the surface of an object by shrinking it down. And it turns out that if you take, let's say, the Earth and shrink it, the gravitational pull becomes stronger on the surface. And if you shrink it to just less than 1 centimeter in radius, then the escape velocity exceeds the speed of light. For the Sun, which is 700,000 kilometers in radius, you have to shrink it to about 3 kilometers. So that's the modern idea, roughly speaking, of a black hole. That number, by the way, 3 kilometers, is the same in Einstein's theory as it is in this simple Newtonian idea. And it's got a name in Einstein's theory. It's called the Schwarzschild radius, after Karl Schwarzschild, who first calculated the way that space and time are distorted in the region of a star using Einstein's equations all the way back actually in 1916, so only months after the theory had been published. And to explain black holes, to talk about them a bit more, I want to show you part of the solution, the mathematical equation that Schwarzschild calculated all those years ago. And I want to show you the part that describes the distortion in time as a result of the presence of a star like the Sun. So I'll show you that equation. Let's imagine there's a clock ticking a long way away from the Sun. So in essentially flat space-time, There's not much distortion out there. And let's say that the rate that time ticks out there is, I'll use the proper language, the proper terminology. I'll call it delta t squared. So delta, the Greek delta, is often used for difference in physics. So that's the rate that time ticks far away from the sun. What Schwarzschild calculated is how the rate that time passes changes as you move towards the star, so into the distorted space-time. So let's put a clock at the surface of the sun, let's say. And let's say that the rate that time ticks there is different. We'll call it delta big T squared. Now, the reason I'm doing mathematics, which is usually a stupid thing to do in a public talk, is because the equation is actually very simple, that describes how the rate that time passes changes as you go in towards the star. Here it is. So for a star the mass of the sun, remember that I said that the Schwarzschild radius, you have to shrink it down to trap light, is 3 kilometers for the sun. So for the sun, this is the factor that tells us how the rate of passage of time changes. R is the distance of the clock from the center of the star, and that's it. So, for example, if we wanted to do the calculation and say, well, how is the rate of passage of time affected by the presence of the sun at the surface, then we'd put R equals 700,000 kilometers. It's the radius of the sun. And we can do the calculation. 1 minus 3 divided by 700,000. It's a very small number. Two things to say. One is it's just less than 1. It's 1 minus something very small. That means that the prediction here from Einstein's theory is that time is passing more slowly on the surface of the sun than it is far away. It's a direct prediction. And if you do that calculation, you will find that it works out at something like a minute per year. So it's measurable, it's appreciable, but you might think, well, it's not a big deal, it's just interesting. The big deal comes if we start to collapse this star down. Remember I said as you shrink the thing down, if you can shrink it to 3 kilometers, then it forms what we'd now call a black hole. It traps light. If a star can behave like that, then this prediction, this equation, starts to predict very strange things indeed. It's so strange, actually, that really until Einstein's death in 1955, I would say, or certainly up to the Second World War, the 1930s, 40s, most physicists, if not all of them, felt that stars would not collapse to form what we now call a black hole. Because Arthur Eddington, actually, one of Einstein's colleagues, great English physicist, but very outspoken, said, he was quoted as saying, nature will prevent such absurdities from happening. That's it, right? Because it's ridiculous. It's actually, incidentally, Oppenheimer, who's been in the news recently, of course, because of Chris Nolan's film, Oppenheimer, just before the war, with a student of his called Schneider, calculated for the first time or showed that under certain assumptions, stars do behave like this. And if a star, at the end of its life, runs out of its fuel and it's sufficiently massive to collapse towards and then inside the Schwarzschild radius, then it will inevitably form a black hole. That was work by Oppenheimer in the late 1930s before the Manhattan Project. So we know that stars do that. And so we have to face the consequences, the strange predictions of this theory. So in order to see what happens, we'll allow the star to collapse. This is what we'd now call a supernova explosion. And as I said, we now know that stars that are 3, 4, 5 times the mass of the sun and above do collapse, and they collapse without limit at the end of their lives. They shrink inside the Schwarzschild radius and they form a black hole. So what's the strange thing about this prediction, if that can happen, and it does happen in nature? Well, let's have a look. The key point is now, so let's imagine this was the sun, something the mass of the sun that collapsed to form a black hole. The key point is, remember we had that clock, and I put it on the surface of the sun, and we calculated that time passes a bit more slowly than it does far away. Now, the sun has shrunk, essentially collapsed out of existence, leaving its imprint in the fabric of the universe behind. That's the description of a black hole in Einstein's theory. It's pure geometry. It's as if you took the star out of the universe, but left a ghost of the star, its imprint in space and time behind. The thing is now, I don't need to stop with my clock at the surface of the star. I can move it further in. So I don't need to stop at 700,000 kilometers, or 100,000, or 50, or 10. I can just keep moving it in. So I could move it into, well, I could move it into 3 kilometers away from whatever this thing is. And now, I hope, you can see the problem. Because that equation, what is that now? That's 1 minus 1, which is 0. So this equation is predicting, this is Schwarzschild's equation, it's predicting that if a star behaves like that, then there is a point in space where, as seen from the outside, time stops. So that seems to be absurd. People got very confused about that. What does it mean? Does it mean that the star can't collapse because I see time stop at a place in space? And also, by the way, there's no point to stop at 3 kilometers. There's no reason why I have to stop at 3 kilometers. There's nothing there. It's just pure space-time. So I could go in to 2 kilometers or 1 kilometer. What happens if I go to 1? Then I've got 1 minus 3, minus 2. What does that mean? Does it mean that somehow time's moving backwards? It's very difficult to understand what this equation is predicting. And that is why historically people found it difficult to believe that this would happen. Well, it does. I've shown you a picture of one. And so what we need to do is we need to investigate what this actually means. And to do that, I'm going to draw a map of the space-time outside and inside the black hole. This point, by the way, I should say, where time stops when viewed from the outside is called the event horizon of the black hole. So what does that mean? So let's draw a map. So just to warm up, what we're going to do is we're going to draw a two-dimensional representation, a map, of a curved surface, space and time curved. Now, we're all familiar with such maps, of course, because we're familiar with maps of the Earth. I'm going to assume everybody accepts the Earth is spherical in here. It's a science festival. I'm assuming no one thinks it's flat. So, given that the Earth is a sphere, then one of the most familiar maps is called the Mercator projection. So that's a map that was developed primarily for navigation. Distortion is inevitable because we're representing a curved surface on a flat surface. But the key thing is that you can choose the distortion so it is useful. It is enlightening or useful in some way. In this case, by the way, the Mercator projection, then straight lines on the map are useful. So the distortion is chosen such that if you draw, let's say you want to sail from Genova to New York, then on this map you draw a straight line, and the angle of that line to the vertical gives you the compass heading you have to sail at to travel between the two cities. So straight lines are important, and the distortion can be chosen so that there's something useful about the map, navigation in this case. So now let's go to the map of a black hole. I'm going to start, well, I should say that the maps that we're going to draw are called Penrose diagrams, named after Roger Penrose, who I think spoke at this festival a few years ago. In the 1960s, Penrose found a way of essentially doing the opposite of this map, the Mercator projection. You think about what this map does. How does it distort the world? Well, it distorts more and more down towards the poles. And actually, just formally, mathematically, if you take a point at the South Pole or the North Pole, then it's not drawn on this map because the distortion is infinite at that point. So these maps, the familiar maps of the Earth, actually take a point at the poles and distort it infinitely along the horizontal axis. The maps that I'm going to show you, that we're going to use to explore black holes, do the opposite. So Roger Penrose found a way of taking infinity and distorting it down to a finite place on the page. And that's very useful because there are infinities all over the place in black holes. So let me show you first the simplest Penrose map, the Penrose diagram. This is a map of an infinite, eternal universe. So already you can see that Roger Penrose has taken infinity and brought it to a finite place on the page. This is every point, every event in a universe that's infinite in space and infinite in time. Time on these maps runs vertically, and space, we've only drawn one dimension of it, but space runs horizontally. So on this map, the bottom point of the diamond is the infinite past, and the top is the infinite future. That's all of time. And then across the horizontal, we have all of space, and the 2 points of the diamond are infinitely far away from each other. So everything that has happened and will happen in an infinite spatial universe, infinite in time, is represented on this map. There's nothing in this universe yet. It's just a completely flat, featureless universe. So that's a Penrose diagram. Now let's put a black hole into the universe. It's going to distort it, curve it, so the map is going to change. And the map changes to this. So this is a very famous Penrose diagram. A Penrose diagram, a map of space and time around an eternal black hole, one that has existed forever in an infinite, eternal universe. So the universe is still here. It's all here, the infinite past and the infinite future. The map's changed because everything's been distorted. And the new feature is this triangle up here. The dividing line between the infinite universe and the black hole is the event horizon, as we spoke of earlier. So that's that place where, as seen from the outside, time stops. And then the other new feature is this thing here, this horizontal line, which is known as the singularity. Now, if you know something about black holes a bit, then you perhaps picture the singularity as this somehow an infinitely dense point, right? The place to which the star collapsed. But actually, using this map, we're going to see that it's rather more interesting than that. And the way we're going to explore it is we're going to send someone into the black hole. So an astronaut, let's say, from the external universe across the horizon into the interior. So this blue line is the path over space-time that the astronaut takes from out of the universe across the horizon into the interior. That line, by the way, it's a very important concept in relativity. That line is called the world line. The world line of the astronaut. And world lines are very evocative things. We teach them right at the start when we teach about relativity. Because we all have a world line. They're personal to us. So if you imagine the moment you were born, you had, let's say you had a little book and a watch. And you started the watch ticking. And at every point in your life, every event, everything that happens to you, you note down the time that it happened and the place that it happened. So you end up with a list of moments in space and time that are important to you. Might be your first day at school, or the day you got married, or whatever it is, the day your first child was born. You note them down. Now you could plot all those points on this map, because this is a map of all of space and all of time. So you could put them there, the events of your life, and you could join them up. And that line would be your world line. So we all have individual world lines. Now they have an interesting interpretation in relativity. So what is the world line? It's actually the time measured on that watch that you carried with you for your whole life. From the moment you're born to, well now, let's say, to this event tonight. What it's measuring is the length of the world line. That's your age. So your age in relativity, the amount of days that you've lived or seconds that you've lived, is, in this theory, the distance you have traveled over space-time during your life. It's a powerful idea. That has an interesting consequence, actually, because let's say that we all decided that we'd come together again next year in this place, another event in our lives. So all our world lines intersect now, and then they'll intersect next year when we all come back again. In the intervening time, though, then we're all going to do different things. We're going to travel to different places. You might go to America or Australia, whatever it is. We all go about our lives and we come back again. That means that all our world lines between now and next year will have different lengths, which means that we will have aged at different rates because we've all traveled different distances over space-time. So your time in relativity is personal to you. Your time always ticks at the same rate on your watch, but if you travel different routes between events in space-time, then you will age differently to people that take different routes. It's not a very difficult concept, really. It's just like if I said, what's the difference between here and Milan? You would say, well, it depends which route you go. Well, the distance between two events in space-time is the amount of time that passes as you travel your path between those events. That's why, by the way, your time is personal to you, why the astronaut can fall in. And we're going to see the consequences of this later. I said, you might be complaining about this, I said that in Einstein's theory, if you look at a black hole over there, then you see time stop on the event horizon. So you might say, well, you'd never see the astronaut fall in. That'd be true from the outside. But from the astronaut's perspective, she's looking at her watch, it's ticking at 1 second per second, and into the black hole she goes. Doesn't notice anything as she crosses the horizon, although we'll talk about that in a few moments' time. So, the astronaut goes into the black hole. What happens in there? Well, the one thing I haven't used yet to explain what happens is, remember I said with the Mercator projection, then straight lines are important. They're lines that aid navigation. That's why the map is distorted in the way that it is. Roger Penrose chose that distortion so that light rays always travel in straight lines on these diagrams. That's what he chose to do. That's why the diagram looks like that. So for example, let's say the black hole's over there and the astronaut's falling in and decides to shine a light beam as a laser straight out of the black hole, away from the black hole. On this diagram, so the astronaut's outside the black hole, away from the black hole is that way. So a light beam would go up at a straight line, and it's arranged on this map so the light beam goes at 45 degrees. And it goes off forever. This is infinitely far away on this diagram. So off it goes, straight line, 45 degrees. If she decides to send the light beam inwards towards the black hole, then on the diagram it goes the other direction, 45 degrees, crosses the horizon, and ends on this line, whatever it is. So inwards, outwards. But now, look what happens when the astronaut crosses the horizon. So let's say she sends the beam inwards, as before, but now from inside the black hole. So inside the black hole, inwards, 45-degree straight line, ends on the singularity. Bang. Look what happens when she shines the beam outwards now. Out, away from the black hole, but inside the horizon. Off it goes, 45 degrees into the future, but now it doesn't go on forever. It also hits this line. the singularity. Can you see that in here, anything that happens, anything that the astronaut emits, anything that comes in across this line is going to end on the singularity? So what do you call something that inexorably lies, well, it lies in the future of everything that crosses this line? That's what this is. Something that lies in the future is a moment in time. It's not a place in space. So the interpretation, which is forced on us by this diagram, is this thing here, the singularity, is not a place in space at all. It's a moment in time. And can you see that there's nothing up here? And so it's not only a moment in time, something in the future of everything that crosses the horizon, it is the end of time. That's why I said that that photograph that we saw at the beginning is a photograph of the end of time. That's what the singularity is. One way to think about what's happened here is that space and time have become so distorted inside the black hole that they've swapped roles. And so what we thought of as a place in space has become a moment in time, the singularity. So this is very strange, you might say. Well, surely this has consequences. We're saying that stars collapse and produce a local end of time in space. What are the consequences for the external universe? There are consequences. And to see what those consequences are, I now have to talk about work that Stephen Hawking and others did in the 1970s. So this is the state of the art before the 1970s. Just to say, this is quite an abstract picture I've given you so far, this map. So I just want to show you what a real black hole would look like if we decided to fly towards one. What does this distortion look like? So this is a simulation of, we're imagining that we're in a spacecraft traveling towards a black hole, and we're going to go into orbit around the black hole. This simulation was carried out using computer code that was developed for the film Interstellar. And it's a direct implementation by Kip Thorne, amongst others, a great Nobel Prize-winning physicist, of Einstein's equations into the graphics software. So the only thing that we put into this simulation was a star field surrounding us. So we're in a spacecraft flying towards the black hole into orbit around it. So a star field surrounding us. And then we put a flat disk of material around the equator of the black hole, just like Saturn's rings. And that disk is known as an accretion disk, because we think that real black holes have material spiraling around them. But it was just flat when we ran the simulation. And then we run the simulation. What you're seeing is all the light rays being traced around the black hole according to the predictions of Einstein's theory. And what you see is some absolutely bizarre behavior as we orbit around it. You see the distortion of the space around the black hole, which is causing these strange effects. You see this characteristic distortion in the disk. What's happening there? Well, what's happening is light from the front of the disk and the back of the disk is being bent around the black hole. It sometimes orbits around the black hole, actually, before it goes off into your eyes. And so you're seeing here multiple images of the flat disk of material around the black hole, sort of entering your eyes from all angles. So you see the whole disk, the rear and the front and the underside and the top. This is a prediction, a direct prediction. Einstein could have made this prediction of what a black hole would look like if he'd had 21st century computers. So a prediction of the 100-year-old theory of gravity, and as we now know, that's a picture of a black hole. So this is a remarkable achievement, first of all. So these things exist, and they look precisely a bit blurry, but it's 55 million light years away, right? So, but they look like the prediction of the theory. So, as I said, these things exist. The prediction of the theory that describes them, and described them all those years ago, tells us that in there lies the end of time. And as we're looking at this thing, the horizon of the black hole, time stops on the horizon. So what are the consequences of that? Well, this is where we come to Stephen Hawking and collaborators in the 1970s. So what Stephen Hawking did was he thought about what that strange behavior, that strange distortion in space and time does to the vacuum of space. Now, vacuum is one of those words that we think of, it means empty, right? It means like there's nothing there. But the other great pillar of 20th and 21st century science is quantum theory. Quantum theory describes everything we know of in the universe other than gravity perfectly, as far as we can tell. And quantum theory tells us the vacuum of space is not empty. So if you could sort of zoom in to a small piece of space, let's say just in front of your face, and we'd removed all the air and everything, so as good a vacuum as we could imagine. But you could slow time down and magnify down. Then a picture of what's happening is that you'd see it filled with activity, filled with particles. And one way you can imagine it, and Stephen Hawking wrote this in his paper, said it's a picture, so it's not exactly accurate, but it's a good picture of what you'd see. You could imagine particles coming into and out of existence all the time, of pairs of particles. They're called virtual particles. These particles are what's called entangled with each other, which is a quantum mechanical term. But entanglement is very important. It's been called the glue that holds space together. So emptiness has a structure, as far as we understand physics. All these particles coming in and out of existence. What Stephen Hawking calculated is what the event horizon does to those particles, the structure of space. And what it can do is it can take those pairs of particles, and it can sometimes be the case that one of them is on the inside of the horizon and one of them is on the outside. Now we know what can happen or will happen to the one that's inside. According to Einstein, it's going to the end of time. Remember, everything inside the horizon goes to the singularity, the end of time. If that's the case, it turns out that the other one, its partner, on the outside of the horizon, can become real and can escape into the universe. So Stephen Hawking calculated that these things, this distortion in space, glow. They emit particles. They have a temperature. Now, so important was that discovery that if you go to Westminster Abbey and look on the floor of the Abbey, you will see Stephen's memorial stone, and chiseled in stone on the floor of the Abbey is this equation, T equals Stephen Hawking's equation for the temperature of a black hole. Now, a couple of things to say about this. One is it's immediately very strange, because remember I said that the black hole, the model of a black hole that Stephen used, is pure space and time. Now, if you go back to the 19th century and you look at the science of thermodynamics, when we first started thinking about temperature, it is a number that we gave to things, something you can measure on a thermometer. But at the time, when the concept first entered physics, we didn't know what it was. It subsequently was understood that temperature is something to do with the moving parts of matter. It's to do with how things jiggle around. It's a feature of things that are made of smaller objects. That's what temperature is. But the black hole is space and time. So immediately, there's a suggestion that there's something interesting about space and time here, because space and time can have a temperature. Related to this, again in the 1970s, and actually historically, initially just before Hawking's work, it was also realized by a student of John Wheeler's called Jacob Bekenstein, that black holes also have what we call an entropy. Now, entropy is also a feature of the structure of matter. It's associated with information. It's associated with how things are structured. And Bekenstein calculated, it was very odd, that black holes can store information. How much information can they store? Well, using a very simple calculation, which was subsequently refined, he found out that, put it this way, if I said how much information is stored in this room, how much could possibly be stored in here, then you would surely say, well, I don't know what it is, but it's something to do with the volume of the room. How many bits of information can I fit in? What was shown for black holes and realized is it's not the case. Black holes do store information, a huge amount of information, but the amount of information is proportional to the surface area of the event horizon of the black hole. It's actually equal to it for the experts in something called square Planck units. That's very, very, very strange indeed. What does that mean? So now we're trying to say that space and time can store information, but they only store it on a surface surrounding the black hole. It's as if almost the black hole doesn't have any interior at all. It's a very odd realization. So this is where we were in the 1970s. These very precise calculations ultimately that told us that black holes have a temperature and they have an entropy, which seems to suggest that they may be made of something. Space and time may be made of something. That's where we are in the 1970s. Now, I'm going to jump forward because we're in the last 10 minutes or so. I want to try and describe to you where we got to with this picture. Let me show you another Penrose diagram. So you don't necessarily need to pay a huge amount of attention to this, other than to say it's going to show us two things. So I've drawn the diagram again of the black hole. But if you think about it, what did Hawking show? He showed that black holes glow. They emit particles. What does it mean to emit particles? It means you're losing energy. You're sending energy out into the universe. So a glowing black hole is a shrinking black hole. That means that one day the black hole will be gone. It will leave the remains of itself in the universe, but all that complicated space and time and twisted things and the end of time, all that goes away. Black holes evaporate. Stephen called his 1974 paper actually black hole explosions. So black holes ain't so black and they don't live forever. That immediately raises a profound question. The question, and it was recognized in the 1980s, is, well, what happens to everything that goes into the black hole then? You can see it here. What I've done is I've drawn the singularity, but the singularity goes away at some point, and space-time returns to being flat again. So these things that went in here, remember, everything that gets emitted, including this thing, all ends on the end of time, the singularity, it's all gone, and then the universe is back again. So the question is, what happened to all that stuff? Did it just get erased from the universe? If it gets erased from the universe, then we have a profound problem. The great physicist Leonard Susskind and his collaborator Gerard 't Hooft, who got a Nobel Prize for particle physics a few decades ago, they said very famously that if this is true, if that stuff completely vanishes, our entire subject, by which they meant physics, is destroyed. The reason is that in everything we know about physics, information is not destroyed. You might say, well, surely it is. What if I get a book and set it on fire, burn the book? Surely the information in the book is destroyed. Well, no, actually. In principle, although not in practice, if you could collect all the ashes from the book, the burning book, and measure everything absolutely perfectly, then you could run time backwards and reconstruct the book. So you can always reconstruct the past from the present, and you can always, in principle, predict the future from the present. It's called determinism, central to physics. But if this diagram is correct, and these things are all getting destroyed, then black holes erase information, determinism is dead. We can no longer do cosmology, basically, because these things that are present in the universe are erasing information, which would prevent us from going backwards to understand what the universe used to be like. We don't know anything about the planets or stars or anything else that fell into the black hole. That's called the black hole information paradox. And there's another problem, actually, which I can show you with this picture. So remember I said that the astronaut, you might have been confused, actually. I said the astronaut freezes on the event horizon from the external perspective, falls into the black hole from the astronaut's perspective, goes to the end of time. Seems like there are two pictures of what's happening here, and it's actually worse than that. So this idea that the black hole glows, that Hawking radiation comes off the event horizon through this process that I described, means that as you go closer to the black hole, it gets hotter. The Hawking radiation gets more intense. And actually, Hawking's prediction from the 1970s implies that if I had a thermometer and I was in a spacecraft hovering above the black hole and I lowered it down towards the horizon, the thermometer would read higher and higher temperatures. And so the implication is that as you approach the horizon, things get very hot indeed and you get vaporized before you fall in. So there's now a contradiction. Does the astronaut going in get vaporized before they reach the horizon? Or, in accord with Einstein's theory, does the astronaut fall through the horizon into the interior of the black hole, as I described? So that both can't happen, you might say. It's a problem. Actually, we now believe that both do happen, right? So the astronaut gets vaporized from the external perspective and gets what we call spaghettified, right? Stretched and squashed, and then goes to the end of time from the astronaut's perspective. Two pictures of the same physics. This has a name. It's called black hole complementarity, and it was introduced by Leonard Susskind and Jared 't Hooft to explain what's happening here. So now we have a very strange picture of the world of physics. We have an idea that there are two different complementary descriptions of what happens in reality. One case, someone gets vaporized. In the other case, they get stretched and squashed and go to the end of time. And we're asked to believe that both are true, both happen. The reason, by the way, that people didn't just laugh and took this seriously was it was proved rigorously that there's no contradiction. There would be a contradiction if someone could stand outside the black hole and collect the ashes of the astronaut when they got vaporized, and then try to jump into the black hole to show the person who's inside their ashes, right? So they say, look, here you are, you've been vaporized. It turns out that you can rigorously calculate that there's never enough time to do that. It is impossible in principle for anyone to make a measurement out here of something that happened and then jump in to compare notes with the person that goes in. So you might think, well, this is just, it's crazy. Who cares about this? It gets even more interesting when we see what the solution to this is. So just in the last couple of minutes, let me give you a flavor of how this has been resolved to an extent, but raised a lot more profound questions. So we have two problems really here, which are related. One is that the thing seems to destroy information, which is forbidden in physics. And the other one is that there are two descriptions of reality. One in which someone gets vaporized and never goes in, and the other one where someone goes in and goes to the end of time. So that was the situation in the 1990s and 2000s, actually. So let me show you, I'm going to skip that one and show you an absolutely crazy picture, which is the picture of what we think is happening now. So in 2019, there were two papers published in which people redid Hawking's original calculation. So they were trying to understand what happens to these particles that kind of get separated on the event horizon, one becoming the Hawking radiation, the other one going into the interior of the black hole. And those calculations suggested, bizarrely, that as the black hole gets older and older, so it shrinks and shrinks, for the experts it means older than something called the page time, but it doesn't really matter, about halfway through its life. As the black hole gets older, what happens is that a region in the inside of the black hole becomes the same region as the outside of the black hole. So you get a kind of a strange, we call it a duality, but a strange idea where the inside becomes the same place as the outside. I've tried to sketch it here. So in this diagram, the orange regions of the diagram, so this is the event horizon of the black hole. These are the Hawking pairs. This is the radiation that comes out and the radiation that goes in. The picture seems to be that wormholes, right, so those things in science fiction, open up between the interior of the black hole and the exterior. And they link these regions together in a way that blurs the difference between the inside and the outside. So what I've colored as orange here in a very old black hole is to be treated as the outside of the black hole. So it's the idea really is that there are two descriptions of reality. And what we're seeing in a black hole is we're kind of seeing them both fighting against each other. What it seems to mean, this, is that space and time themselves are being built up out of smaller bits, which is what I said initially from those 1970s papers. These bits are entangled together. They're quantum mechanical objects, whatever they are. They're entangled together. And that entanglement manifests itself as wormholes connecting distant regions of the universe with the interior of the black hole. So this is how the information's getting out. The picture really is that if you jumped into a black hole, what would happen is you'd be scrambled up. And before you reach the singularity, you'd essentially meet a network of wormholes, and your scrambled bits would emerge back out into the universe again. Information is conserved, and everyone is happy. It's a very strange picture of the world, though. Really what it seems to be telling us, and this is where I'd like to finish, is that space and time are not fundamental. And I think that's a remarkable thing. Einstein was quoted, this beautiful quote. He said, if you pay attention to the universe very carefully, to nature, any piece of nature, really carefully, and you observe it and you keep pulling at the intellectual threads and you won't let go, you want to understand it, you have a chance of glimpsing something deeply hidden. It's a very beautiful phrase. Catching a glimpse of something deeply hidden, which is the deep underlying structure and beauty of nature. And what we've learned in the last few years, and we don't fully, the reason I'm being vague is because we don't fully understand this picture, but what seems to be the case is that by studying black holes, trying to understand what happens to things that fall in, how information gets out, we're beginning to see that space and time have a deeper structure. That's the something deeply hidden. They're emerging somehow from entangled quantum objects, and those are manifesting themselves as these strange geometries and curves and warping of space and time. So I hope I've tried to give you just a flavor, most of the talk, the Einsteinian picture of the strangeness of black holes. But at the end of the talk, I brought you to 2022 or 2023, where we're beginning to suspect that even the notion of here and there, this place being close to or far away from that place, appears to be an approximation to the underlying structure of reality. So with that, thank you very much. Happy to answer questions. Thank you. Oh, thank you. Thank you very much. Thanks. I think we've got time, I think, for a couple of questions, haven't we? One or two questions. So does anyone have a question? If it's in Italian, that's fine. It'll be translated. Or you can ask. Do we have a microphone? Or? I prefer English, but I can. Okay.
Told me to speak in Italian.
Yes.
Ho capito molto bene la questione, l'entanglement e il fatto che praticamente particelle della radiazione di Hawking che cadono, diciamo la controparte che cade all'interno rimane entangled con la parte esterna e quindi crea un wormhole. Quello che non ho capito è questo. Maldacena parla di isole nei black holes, cioè l'entanglement arriverebbe soltanto tra particelle che sono all'interno di altri black holes.
Yeah.
Perché? Questo non mi è chiaro.
I think I might have understood. I think you were talking about Maldacena. So what I didn't do, I skipped over it. Let me answer this question. So in 1997, a physicist called Maldacena published what is the most cited paper, which means the most used paper to date in this area of physics. It's called the ADS-CFT conjecture. Essentially what it says is that in a very specific model, there are two descriptions, as I mentioned, of what's happening. So you can imagine just quantum theory, nothing else, on a boundary. So this cylinder represents a quantum theory living on the cylinder. And there's a dual description, another description of that world, which is the interior of the cylinder. And so in a particular case called anti-de Sitter space, it doesn't matter what it means really, in a particular case, Maldacena proved that there are two descriptions of a world, one just quantum mechanics and the other one gravity. And actually, he showed, or it was subsequently shown, that this quantum theory can describe a black hole that forms and then evaporates. And because the quantum theory conserves information, then however this black hole forms and evaporates, information is conserved. And this was what forced Stephen Hawking to concede a bet that he'd made years before, where he said that he thought black holes destroyed information. When he saw this picture, Maldacena's picture, he conceded and said, no, they don't, and conceded the bet. Now, I think what your question was related to this. So what I've drawn here, so you can take a picture of it, is that space again. This is really fascinating, though. So what I've drawn here, I've labeled those two lines on the left and right, L and R. These can be seen as two separate quantum theories, just minding their own business. It turns out that if you allow those theories to become entangled with each other, then you generate this space-time. This space-time, the top bit is a black hole, and the bottom bit is actually what's called a white hole. So it's going to be in some sense the opposite of a black hole. So in here, anything that's in here, remember that on these diagrams, light always goes 45 degrees into the future. So anything in here comes out, anything that goes in there goes to the singularity. So this is a complete space-time which describes essentially a wormhole. So it describes a black hole, a wormhole here, and a white hole. So it's a classic, it's this picture actually, the classic wormhole of science fiction. The key point, which I think was your question, is that this exists only if this theory is entangled with this theory. And so the idea is that quantum entanglement builds space and builds wormholes. And there's a theory, actually, an idea called ER equals EPR, again down to Leonard Susskind. An idea called ER equals EPR, again down to Leonard Susskind, which is ER is Einstein-Rosen. Einstein and Rosen in 1935 published a paper that first described a wormhole. As far back as that, 1935. EPR is Einstein, Podolsky and Rosen. They published a paper not long afterwards, actually, talking about quantum entanglement. And the idea is that quantum entanglement is basically, or can be pictured as some kind of wormhole connecting particles together. And some of that evidence comes from images or ideas like this, which go back to Maldacena. So I think, was that your question? So, yeah, so see, I understood. So it's a very, what I would say about this, I should perhaps have talked about it, I skipped over it. This is part of the key evidence that what you're seeing, what I'm saying here is space. There is no, if you have no entanglement between those two theories, this picture is just two black holes. It's separated from each other, essentially in different universes. And if you allow entanglement, then you link them together with a wormhole. So it's an example in a very specific model of space being generated by quantum entanglement, which is what we think the deep message of this physics is. Is that enough for everybody? Any more questions? Oh, there's one at the back there, I think.
Mine is probably a simple question. I was thinking about the diagram with not just one black hole, but different ones. And then I questioned myself if black holes actually could fall one into the other. And so maybe the more basic question is, can black holes actually move?
Can they fall into each other?
Yes, and
Yes.
move in general.
Yes, so that's one of the recent observations we've made. So we've seen black holes collide and merge. We've seen them in an experiment called LIGO and Virgo, which are two so-called gravitational wave experiments. So we've seen the ripples in the fabric of the universe, the waves, caused by the collision and merger of black holes. And what's wonderful is even in those early measurements that we've made in the last few years, we've been able to see that some of Stephen Hawking's original ideas about black holes merging together and the area of event horizons never decreasing in collisions, which is, if you know any thermodynamics, should ring bells. It's like entropy always increasing. We've seen that in that data. So the answer is yes, we see them collide rather more often than we'd expected, actually, in the universe. And they just form a bigger black hole. So that's what happens. They merge together to form another black hole. Right, wonderful. I think that's it, isn't it? Can I just say thank you? I'm so delighted that so many of you came, and I hope you enjoyed that strange talk about black holes. Thank you very much. Thank you. Thank you.